Hi everyone, my name is Jose Lopez, and today I will present our work, Ensemble of Complementary Anomaly Detectors under Domain-Shifted Conditions. My co-authors are Georg, Paulo, Pradyumna, Juan, and Hector. Today I'll begin with a bit of background before discussing the data that we worked with, the models we developed, our results, conclusions, and future work. The work I'm presenting today is a result of our participation in the DCASE 2021 Challenge, which is the 7th edition of the IEEE Audio and Acoustic Signal Processing Challenge on detection and classification of acoustic scenes and events. Participants can take part in any of 6 tasks. The task that we participated in is Task 2, which is anomalous machine sound detection under domain-shifted conditions. This task builds on Task 2 from DCASE 2020 by adding domain shifts, or recording differences between the training and the test data. There is also an additional machine category. Like last year, models are ranked using the area under the curve and partial area under the curve metrics. This year, a harmonic mean is used instead of the arithmetic mean to aggregate scores. What this means is that the scores tend to be dominated by the lower scores, so it tends to present a pessimistic view of the performance of models. Superficially, the data looks the same as last year. There are 10-second audio clips, single channel, recorded at 16 kHz. There are 7 machine types: fan, gearbox, pump, slider, toy car, toy train, and valve. Instead of machine IDs, which corresponded to specific machines, there are now section IDs, which correspond to domain shift types between domains, and they may include more than one machine per section. There are 2 domains per section, source and target. The source domain contains sufficient training clips, while the target domain only includes a few training samples. The data are partitioned into 3 subsets. At the start of the challenge, participants are provided with the development subset, which contains training and testing files for sections 0, 1, and 2. Later during the challenge, an additional subset is released, which contains training files for sections 3, 4, and 5. However, the evaluation subset is not provided to participants, and it contains the test files for sections 3, 4, and 5. A high-level view of our submission is that it contains 3 models and 1 ensemble. 2 of the models are variants of the model that we used in last year's challenge, which consisted of a 2D CNN encoder and an XFactor based classifier. We essentially were treating spectrograms as images. The first variant that we use this year replaces a 2D CNN encoder with a 1D CNN encoder. We did this because we saw that we obtained better performance this way. The second variant operates on the audio directly and uses a WaveNet-based encoder. For both of these models, we self-supervised using the section IDs. The third model is a normalizing flow-based model that ensembles several conditional density estimators, and it accepts at the input pre-computed MEL spectrograms, and it is completely unsupervised. Due to the different input modalities and training approaches, we call these models complementary. Additionally, these models offered strong performance for a subset of the machines, so that even though individually they did not rank very highly, the ensemble of the 3 obtained first place in the challenge. So this slide describes the first variant, which we call XFactor 1D. The diagram on the top right shows the architecture. We accept an audio at the input, and we convert this to a spectrogram using the PyTorch package NN Audio. We like this package because it very closely matches the spectrograms produced by LibRosa. However, we have the option of using a GPU with this package. After the spectrogram is computed, we send it to a standardizer, which this block means it can either be a batch norm layer with the trainable parameters turned off so that way it performs frequency-wise normalization, or it can be an auto dial layer. At the beginning of this challenge, we performed a literature review of domain adaptation approaches, and we went with auto dial because we found it to be, at least in our implementation, more efficient and easier to experiment with while performing similarly to more complicated approaches. So after the standardizer, we send that spectrogram to the encoder, and we have the parameters, the layer specifications on table 3. After this, the embeddings go to the XFactor classifier, which has an additive margin softmax top layer. Table 4 shows the various hyperparameters, the batch size, the spectrogram parameters, and the performance. What I would like to highlight here is that this model performs very strongly for valve, and it performs strongly for gearbox, pump, slider, and not so great for fan and the toy machines. Table 5 shows the relative change in performance when we include an auto dial layer, and we see that we get an improvement for all the machine types except for toy train. We generally trained using the LMW optimizer with the default learning rate and a small amount of weight decay. For gearbox, we found a slight improvement by using averaged stochastic gradient descent. The second variant used a WaveNet-based encoder, so it processed audio directly. It used a single WaveNet block with 14 layers and used 32 channels for the residual, dilation, and skip connections, except for gearbox and pump, for which it used 64 channels. Additionally, the valve machine type benefited from using an autodial standardizer, and we also experimented with data augmentation, in particular with the Tiger-Kaiser energy operator. We felt that its noise suppression capabilities would benefit valve, which has time-sparse, impulsive sounds. However, we saw that toy train also benefited from this augmentation. And table 7 shows the relative change when including these two things. Table 6 shows the performance of this model, which we trained using AtomW again with the default learning rate and a small amount of weight decay. What I want to highlight here from the performance table is that this model performed strongly for fan. It did okay for gearbox, pump, slider, and valve, and not very well for toy train and for toy car. We call the third model NFCD because it is a normalizing flow-based conditional density estimator ensemble. It was implemented using the Pyro probabilistic programming library for PyTorch, and it started out as an attempt at estimating the density of the individual melbins. However, due to numerical issues during training, it evolved into estimating the density of a subset of the melbins conditioned on the remaining melbins. For simplicity, and due to time constraints, we simply took adjacent 32-bin segments with no overlap. And so at the input of this model, we accepted a 256 melbin spectrogram, which was computed using the hyperparameters shown here. And we standardized this spectrogram using a batch norm layer with the learnable parameters turned off. One of the issues we encountered during training is that if one of these estimators diverged, it would derail the training for the entire ensemble. And in order to stabilize the training of the ensemble, we found it beneficial to compute the mean along the time axis. And so the input to the estimators was a vector of the same size as the number of melbins. To obtain the training loss, we simply summed the output of the estimators, which was the log likelihood, and this loss also served as the anomaly score. The training optimizer we used is the same as the previous models. However, we found that this model needed much fewer epochs to obtain the best results. Table 8 shows the scoring results of this model, and I would like to highlight that its strongest category is toy car, and it also performed well for toy train, fan, gearbox. This model was the weakest. The weakest categories for this model were the strongest for the previous models. The last part of our submission was an ensemble of our 3 models. In order to obtain the best weights for combining the anomaly scores of the individual models, we searched over a grid of convex combinations, and we obtained the weights shown on table 11, which also shows the performance of the ensemble. This slide shows the performance of the ensemble on the development data and on the evaluation data. The second row shows the baseline scores for reference. We see that the ensemble performed very well on the development data and nearly as well on the evaluation data, but there was some drop off for fan and to a lesser extent for gearbox. One of the learnings that we took away from this year's DCASE challenge is that existing domain adaptation approaches, especially from the computer vision community, do not seem to work as well for audio. We found that ensembling remains a good option even for domain shifted conditions. Out of the 3 approaches that we worked with, we find NFCD particularly promising because it is completely unsupervised and it is very, it's an advantage to not have to deal with metadata, for example, for self-supervision when applying to practical situations. We also believe that its ensembling architecture will perform well, more robustly, even under domain shifted conditions. So going forward, we plan to investigate this model further and see how we can improve it. And now if there are any questions, please feel free to ask, and I will do my best to answer them. And thank you for your time.